Assalamu alaikum. My name is Rukma Iftihar from the Department of BS Biotechnology and my roll number is 009. Today I am going to give you a detailed presentation on the topic of heterogeneous equilibrium using concept of equilibrium constant. So before starting the topic, we must know the definition of chemical equilibrium. So what is a chemical equilibrium and how do we achieve a chemical equilibrium? Chemical equilibrium is achieved when rate of forward and reverse reactions are equal, the concentration of reactants and product remain constant. Further, chemical equilibrium is defined by K. The magnitude of K will tell us if the equilibrium reaction favors the reactants or the product. If K, that is equilibrium constant, is greater than 1, then the reaction is in the favor of product, and if K is less than 1, then it favors the formation of reactants. Now coming towards the equilibrium constant expression, equilibrium constants can be expressed using Kc or Kp. Now what is Kc? Kc uses the concentration of reactant and product to calculate equilibrium constant. And what is Kp? Kp uses the pressure of gaseous reactants and product to calculate the equilibrium constant. Now we are able to define heterogeneous equilibrium. What is heterogeneous equilibrium? It arises from reversible reactions involving reactants and product that are in different phases. It can include solid, liquid or gas as either reactant or product. It omits pure liquids and solids from equilibrium. So why does it omit liquids and solids from equilibrium? The reason is that the concentration of a pure liquid and pure solid is defined by its density, which can be expressed in units of molarity. The concentration of a pure solid or liquid will not change because its density is constant at given temperature. Its further explanation is given in the coming slides. Now coming towards the example of calcium carbonate, when reaction is carried out in a closed container, three phases are present at equilibrium: solid calcium carbonate, solid calcium oxide and gaseous carbon dioxide. If pure solids and liquids are present in the equilibrium chemical reaction, then the concentrations are not included in equilibrium constant expression, because concentration in equilibrium equations are ratios of experimental concentration to standard state concentrations. The ratio used in equilibrium expression for a pure solid is equal to 1 because standard state of a pure solid is the pure solid itself. Similarly, standard state for a pure liquid is also the pure liquid, giving a ratio of 1. Therefore, equilibrium equation simplifies omitting concentration of pure solids and liquids. The analogous equilibrium equation in terms of pressure is Kp is equals to PCO2, where PCO2 is equilibrium expression of pressure of CO2 in atmosphere. To establish equilibrium between solids CaCO3, solid CO, and gaseous CO2, all the three components must be present. It follows from equation Kc is equals to CO2 and Kp is equals to PCO2. However, this concentration and pressure of CO2 at equilibrium are constant, independent of how much solid CaO and CaCO3 is present. If temperature is changed, concentration and pressure of CO2 will also change because Kc and Kp are temperature dependent quantities. Now, as we have discussed the equilibrium constant, its expression and its values, now the question arises, why we use equilibrium constant? We use equilibrium constant because knowing value of equilibrium constant for a chemical reaction, let us judge the extent of a reaction, predict direction of a reaction, and calculate equilibrium concentration from initial concentration. Let's look at each possibility. Judging extent of a reaction. The numerical value of equilibrium constant for a reaction indicates the extent to which a reactants are converted to product. That is, it measures how far the reaction proceeds before the equilibrium state is reached. Considering the example of H2 and O2, both are in gaseous form and they give the gaseous water as a product. Consider, for example, the reaction of H2 with O2, which has a very large equilibrium constant. Kc is equals to 2.4 to 10 to the power 47 at 500 Kelvin. Because product appear in the numerator and equilibrium constant expression and reactant are in denominator, a large value of Kc means that the equilibrium ratio of product to reactant is very large. This is in judging the extent of a reaction. This is the case of a large value of Kc. Now discussing the small value of Kc. In other words, reaction proceeds nearly to completion. For example, if stoichiometric amounts of H2 and O2 are allowed to react and H2 is equals to 0.10 molar at equilibrium, then the concentration of H2 and O2 that remain at equilibrium are negligibly small. H2 is equals to 4.4 into 10 to the power minus 17 molar and O2 is equals to 2.2 to 10 to the power minus 17 molar. By contrast, If a reaction has a small value of Kc, the equilibrium ratio of product to reactant is very small and the reaction proceeds hardly at all before equilibrium is reached. For example, the reverse of the reaction of the H2 and O2 gives the same equilibrium mixture as obtained from the forward reaction, that is H2 is equal to 4.4 into 10 power minus 17 molar and O2 is equal to 2.2 into 10 power minus 17 molar and water is equal to 0.10 molar. The reverse reaction does not occur at any appreciable extent, however, because its equilibrium constant is so small, Kc is equal to 1 over Kc is equal to 1 over 2.4 into 10 to the power 47 is equal to 4.2 into 10 to the power minus 48. If reaction has an, now we have discussed firstly the large value of Kc, secondly the small value of Kc. Now there comes the turn of intermediate value of Kc. If reaction has an intermediate value of Kc, say a value of range of 10 to the power 3 to 10 to the power minus 3, then the appreciable concentration of both reactant and product are present in the equilibrium mixture. The reaction of hydrogen with iodine, for example, has Kc is equal to 57 at 700 Kelvin. If equilibrium concentration of H2 and I2 are both 0.010 molar, then concentration of hydrogen iodide at equilibrium is 0.075 molar, as you can see in the figure. Thus, concentration of both reactant and product 0.10 molar and 0.075 molar are appreciable. So we have discussed the three possibilities in judging the extent of a reaction. Now coming towards the generalization of these extent of a reaction. What happens if Kc value is greater than 10 to the power 3? Product predominate over reactant. If Kc is very large, the reaction proceeds nearly to completion. Then what happens if Kc is less than 10 to the power minus 3? The reactant predominate over product. If Kc is very small, then the reaction proceeds hardly at all. And what happens if Kc is equal to 1? If Kc is equal to 1, appreciable concentration of both reactant and product are present at equilibrium. Thank you for your time and attention. This is a brief introduction of heterogeneous equilibrium using concept of equilibrium constant.